Good morning, students. Today we are going to discuss stereochemistry of organic compounds. Organic compounds having same molecular formula but a different structural formula are called as isomer, and the phenomena is called as isomerism. Isomers have different properties. There are two main types of isomerism. First is structural isomerism. Second one is geometrical isomerism. First we are going to discuss structural isomerism in detail. So what is structural isomerism? When isomerism is due to the difference in the arrangement of atoms within the molecule without any reference to space, the phenomena is called structural isomerism. Structural isomerism is further divided into 5 types. First is chain isomerism, second is positional isomerism, third one is functional isomerism, fourth one is metamorism, and last one is tautomerism. Now we are going to discuss what is chain isomerism. Chain isomers differs in the order in which the carbon atoms are bonded to each other. For example, butane and isobutane. In a butane and isobutane, we see that it is normal butane molecule, while in isobutane we see that there is a branch here. Both compound, that is butane and isobutane, contain 4 carbon, three, 6, 2, 8, 10 and 10 hydrogen. So molecular formula for both the compound can be written as C4H10. Compound containing same molecular formula but different structural formula are called as isomers, and these two are chain isomers of each other because they are differ in order in which carbon atoms are bonded. Now we are going to discuss what is meant by positional isomerism. Positional isomers differs in the position of functional group on the carbon chain. For example, just see the structure of 1-bromobutane. Here bromine is attached to first carbon atom. In a 2-bromobutane, bromine is attached to second number of carbon atom. They both are isomers of each other. Since position of functional group, here it is halide atom, are different, that's why they are positional isomers. In this case, bromine attached to first carbon atom. In this case, bromine attached to second carbon atom. Also see the example of 1-butene and 2-butene. In this case, the double bond, that is functionality, is present in between first and second carbon atom. In 2-butene, functionality present in between 2 and 3rd carbon atom. So they are positional isomers of each other. Third type is functional isomerism. Functional isomers differs in nature of functional group. It is important. For example, ethyl alcohol and dimethyl ether. If we write molecular formula for ethyl alcohol and dimethyl ether, it comes as C2H6O. But in ethyl alcohol, functionality is OH. In dimethyl ether, functionality is COC. That's why they are functional isomers of each other. Also see the example of acetone and propanaldehyde. In this case, functionality is ketone. In this case, functionality is aldehyde. Now we are going to discuss the topic of metamorism. In this type of isomerism, there are unequal distribution of carbon atoms in either side of functional groups. Member belongs to same homologous series. It is important. Just see example of diethyl ether and methyl propyl ether. In both compound belongs to ether family. But if we in dimethyl ether there is 2 carbon atom present on left hand side as well as right hand side, while in methyl propyl ether your left hand side have 1 carbon atom while right hand side have 3 carbon atom. They are metamers of each other. Also see the example of diethylamine and methylpropylamine. Both compounds belongs to amine family, but in the first compound on your amine functional group, left hand side contain 2 carbon atom, right hand side also contain 2 carbon atom, while in this case left hand side contain 1 carbon atom while right hand side contain 3 carbon atoms. That's why they are metamers of each other. Now we are going to discuss Tautomerism. It is the special type of functional isomerism in which isomers are in dynamic equilibrium with each other. For example, ethyl acetoacetate is an equilibrium mixture of two forms. At room temperature, the mixture contains 93% keto form plus 7% of enol form. So this is the formula of acetoacetic ester. So in this formula we see that it is the keto form of acetoacetic ester and it is in dynamic equilibrium with enol form of acetoacetic ester. How it can be written? It can easily be written by shifting this bond here and hydrogen from here, shift the one of the hydrogen from here to on this oxygen. Now we are going to see what is meant by stereoisomerism. When isomerism is caused by different arrangement of atoms or groups in a space, the phenomenon is called stereoisomerism. The stereoisomerism have same structural formula but different arrangement of atoms in a space. There are two types of stereoisomer. First is configurational isomers, second one is conformational isomers. Now we are going to discuss the topic of configurational isomers in detail. The different special arrangement of atoms in a molecule which are not interconvertible without breaking of bonds are called as configurational isomers, and the isomerism exhibited by them is called as configurational isomerism. Configurational isomers can be separated. There are two types of configurational isomerism. First is optical isomerism, second one is geometrical isomerism. First we are going to discuss topic of optical isomerism in detail. Before understanding optical isomerism, we have to understand some concept related with optical isomerism. The first concept is of optical activity. What is meant by optical activity? Ordinary light is composed of rays of different wavelength vibrating in all directions perpendicular to the path of its propagation. When ordinary light is passed through the polarizing nickel prism, the vibration occurs in single plane. Such a light whose vibration occurs in only one plane is called plane polarized light. Compound which rotate the plane polarized light is called optically active compound, and this property is called optical activity. If the compound rotate plane of polarization to right, that is clockwise rotation, it is said to be dextrorotatory, and it is denoted by this, that is plus sign or small d. If the rotation is to the left, that is anti-clockwise, the compound is said to be levorotatory, and it is denoted by this negative sign or small l. So just see, this is the source of light. It is the ordinary light. When this ordinary light is passed through nickel prism, we got polarized light. When this polarized light is passed through a solution of compound containing chiral carbon, the plane of polarized light, it's shifted towards, in this case, right hand side. So this phenomenon is basically known as optical activity. Now just see, when this plane is shifted from its original position, there is a creation of angle. What this angle means, now we see it. Now what is meant by specific rotation? Optical active compounds rotate the plane of polarized light. The degree of rotation depends upon the number of molecules of the compound encountered by a light along its path. It is therefore necessary to introduce some standard by which rotating powers of different compounds may compare in terms of specific rotation. Specific rotation is defined as the rotation produced by a solution of a length 10 cm and unit concentration, that is 1 gram per ml, for a given wavelength of a light at a given temperature. Consider a safe stream in which plane polarized light is rotated through alpha degree at a temperature T degree centigrade and using sodium D light as a source. The specific rotation therefore can be written as into bracket alpha bracket close to the power T, and rotation by this symbol is given by alpha TD is equal to 100 multiplied by alpha divided by L multiplied by C, where L is length of tube in decimeter, C is the number of grams per 100 ml of solution. The specific rotation varies with both wavelength of light and temperature. In our next class, we are going to see elements of symmetry and some other concept. Thank you very much.